The laptop communicates with the Ultra using a TCP socket. In my code, the laptop connects to localhost port 8888. Since the Ultra is remote, I use SSH local port forwarding, so traffic is tunneled to the Ultra. Messages are sent using JSON over TCP, with each message ending in a new line character, so packets can be separated at the receiving end. The laptop sends an inference request containing the frame ID and the field sensor window. The Ultra responds with a inference response containing the same frame ID, the dummy predicted gesture, and the confidence score. The inference response is sent back to the laptop. The send JSON line function converts the message into JSON and adds a new line delimiter and sends it through the TCP socket. Comms between the laptop and the visualizer is done with MQTT over TCP, with the laptop acting as the broker. So the broker address is set to localhost, and gesture results are published to this topic. The visualizer will then subscribe to the same topic, and when the Unity client connects, this onConnected function will be called, and it will subscribe to the topic. Whenever a message arrives, this decode message function will be called, and we will pass the JSON message into a gesture data object. Messages sent have the JSON format shown with a type field, frame ID, gesture ID, and the confidence value of the prediction. I use a fixed device ID per port, 1 for the hand device and 2 for the leg device. Device ID is included in every outgoing packet from the ESP32, so the laptop can identify which device sent it and route the packet to the correct queue. For packet types, for the FireBeater to the laptop, we have the hello packet, which purpose is to identify the device after connection. For the laptop to the FireBeater, we have a command packet, which controls the device behavior like triggering haptics and start and stop the streaming of data. Finally, there's also the packet for the sensor data. All packets are transmitted as JSON objects with TCP over Wi-Fi. An example is this packet sent from the leg device. It has the type field, device ID, timestamp, and the IMU measurements. Each packet is separated by a new line so the receiver can pass it. Comms between the ESP32 and the laptop is encrypted using TLS over Wi-Fi. On the ESP32, we use the Wi-Fi client secure class, which provides TLS encryption for all TCP communication. This line, set in secure, disables the cert verification. So the ESP32 don't check the server certificate, but the connection is still encrypted with TLS. On the laptop side, the server creates an SSL context and wraps the TCP socket. And this will convert the socket into a TLS encrypted connection. Comms between the laptop and the Ultra is secured using an SSH tunnel. This command creates a tunnel that forwards the laptop port 8888 to the Ultra port 8888. So the laptop connects to localhost and the same port, and SSH will encrypt and forward the data. On the Ultra, TCP server listens on the same port and creates a connection socket after accepting the laptop connection, and all data is transmitted through this connection socket. MQTT payload is encrypted with AES CBC mode with a 32-character shared key. Each ASCII character is 8 bits, so 32 characters will give 256 bits. A random 16-byte IV is generated for every message, and the plain text JSON is padded with PKCS7 to a multiple of 16 bytes, and then encrypted with AES 256 CBC mode. The IV is prepended to the ciphertext, and the combined bytes are base 64 encoded, so it can be sent as a normal MQTT string payload. On the visualizer, the Unity receives the encrypted base 64 string and then it extracts the IV and the ciphertext and decrypts the message using the same key. Padding is automatically removed. This table is a summary of the codes that run concurrently. First, the except ESP32 loop thread will continuously listen for incoming ESP32 TLS connections. When a device connects, it will send a start command, and the ESP32 will send a hello packet with the device ID. This to identify whether the device is the hand or the leg unit. It then stores the active socket inside the device sockets dictionary, which is keyed by the device ID. This will allow the program to track which devices are connected and also handle reconnections by replacing the old socket. Finally, this thread will spawn a ESP32 receive thread for the device, which can be the hand or the leg device. The ESP32 receive thread will continuously receive new line delimited JSON packets, pass the sensor data, and push the extracted features into the respective queues, which is the hand samples or the leg samples queue. Since these queues are shared across threads, they are protected using hand lock and leg lock. After pushing a new sample, each receiver thread will call the fusion condition notify all function, and this will wake the fusion thread. So it will avoid busy waiting and will ensure that the fusion thread only runs when new data is available. So the fuse and send thread is responsible for combining data from both devices. It waits on the fusion condition, and when it wakes up, it checks that both devices are connected and that both devices and both queues have data. It then pops one sample from each queue, fuses them, and accumulates them in a 50 sample window. Once the window is full, it sends an inference request to the Ultra 96 and sets a in-flight request event flag. This flag will act as the flow control so that only one inference request is running at a time. Finally, the Ultra 96 receiver thread will listen for the inference response from the Ultra 96. When a response is received, it publishes the result to MQTT and clears the in-flight request flag and notifies the fusion thread again. This allows the next fuse window to be sent only after the previous response have been received. So I first run the SSH tunnel, and then I start the MQTT broker. Now I'll start the Ultra server and the relay laptop script. As you can see, the two devices have started to connect, and it will start sending data to the Ultra 96, which will wait for 10 seconds to simulate the inference time, and this Ultra server will send it back to the laptop, and the laptop will publish it to MQTT. On my phone, you can see that it can receive data. Now when I print a packet from the hand device, you can see the device ID and the sensor data. As you can see, the FSR value is 255. So once I press on the sensor and print the packet again, the FSR changed to 0. I can also trigger haptics on the hand sensor. And similarly for the leg device, I can print a packet, and when I change the orientation of the leg device and print the packet again, you can see that the value has changed.